Brilliant. Okay, so I see Professor Lucas. Professor Lucas Cardelli is here. So if you can upload your presentation, that would be great. I also want to check in the audience. Professor Daiba, are you here?
Yes, I'm here.
Brilliant. Okay, thank you. You will be the next. So
Okay.
we're running slightly late. Sorry about of the procedure. Probably it's a bit long because of we had some issues.
No.
Okay, thank you very much. Okay, so yeah, Luca, we can see your presentation.
I hope you can hear me as well.
I can hear you as well. I'd like to introduce Professor Luca Cardelli, who is a fellow of the Royal Society, ACM fellow, member of the Activia Europeana, member of AITO, a long-standing member of EATCS, Royal Society research professor in Department of Computer Science at University of Oxford. So the floor is yours, Luca.
Right, great, thank you. Thanks for the introduction. Today I want to talk about chemical reaction networks and their role in digital and analog computing. So a chemical reaction, I'm sure everybody has seen them in school. There are things like this, like X plus Y goes Z plus W at some rate R, which is represents the speed of the reaction in some way. And these chemical reactions are traditionally they've been a phenomenological model, meaning that people would study nature and see what kind of reaction happened in nature, and they would write them down. But that was only basically recording what nature was doing. But increasingly today, we can actually go the other way around and write chemical reaction as programs, and then cause these programs to execute even in nature, in the physical reality. Chemical reaction networks are also a programming language in a sense. In fact, in our genomes, there is some kind of coding of chemical reactions that happen in the cell. So there is somewhere a programming language there for chemical reactions. Also, chemical reaction networks are mathematical structures which have been rediscovered in many forms. They are called vector addition systems, Petri nets, bounded context-free languages, population protocols. They're all slight variations of the same theme, and they've been analyzed in many different ways. In general, these are description of mechanisms. So a reaction is like an instruction. It tells you what happens at each step. So describe mechanism rather than behavior. And behavior you can describe by equations like differential equations, and the two, of course, are related in very precise ways. So I want to try and convince you, first of all, that the chemical reactions are a programming language. You can actually write programs. And I will just go through some very simple examples. So suppose you have so Y and X will be populations of molecules, let's say. There could be populations of agents, populations of whatever you want, but it's a collection of uniform entities. And suppose you want at the end of your program to have twice as many Y's as you had X initially. So this is the specification of doubling X. Well, you can write this chemical program that says, for each X, I produce 2 Y's, and you're done. Similarly, you can divide by 2 by taking 2 X's and producing only 1 Y, modulo the fact that this has to be even now. And if you want to sum two collections of entities, you can just send X1 to Y and X2 to Y. So this means that X1 is removed and Y is added, X2 is removed and Y is added. So at the end, you get the sum of X1 and X2 into Y. Little bit more interesting is the minimum function. So the mean of X1 and X2 you can achieve by this instruction here. X1 plus X2 goes to Y, because whatever is the smallest population, it will run out first. And when this population runs out, let's say X1, then this reaction can no longer execute. And therefore, you get as many Y's you had X1, which was a small population, or vice versa for X2. So this does the minimum in a single instruction. But if you want to do the maximum, it's not so easy. Now you get to see a real algorithm here. So we're going to need the property that the maximum of X1, X2 is, in fact, the sum of X1, X2 minus the minimum of X1, X2, a simple algebraic law. And so we're going to try to implement this expression here in chemical reactions. So first we do this sum, x1 plus x2, by sending x1 to y and x2 to y. We also at the same time copy x1 to L1 so we don't lose it, and copy x2 to L2. Then we do the minimum, we've just seen that, L1 plus L2 goes to k. And then the subtraction, which is y plus k goes to 0, to nothing, because we actually know that y is bigger than k, so we can do it in a single instruction. So as you can see now, this is a program, and it's running concurrently. All these reactions are running concurrently. So the correctness is not completely trivial, but you can work on that and convince yourself that it works. Next is an even more interesting algorithm. This is a consensus. We just had a talk about consensus algorithm. So this is a consensus algorithm called approximate majority. And the idea is that there are two populations of entities or molecules. And at the end of the algorithm, you want the biggest population to win. You want all the populations to flow into the biggest one. So if x is greater than y initially, then at the end of the execution, you want the whole population on the left-hand side and nothing on the right-hand side. Conversely, if y is greater than x, then at the end you want all the population on the right-hand side instead of the left-hand side. And if they're equal, then both these things apply, and then there will be some kind of random choice that happens. It's an inherently stochastic algorithm. So the way to implement this algorithm is with chemical reactions is written here. The idea is that one molecule of X meets one molecule of Y, and they have no idea who's in majority. So one of them becomes undecided. In the first reaction, X becomes undecided, which is this B species. In the second reaction, Y becomes undecided, symmetrical. And then if an undecided molecule meets X, it thinks, well, I just met an X, so it's likely that there are more X's than Y, and so it follows X. But if it meets Y, it reasons, well, I met a Y, so it's likely there are more Y's than X's, and then it follows Y. So this is it's actually an optimal algorithm. It's not just a simple one, so it's even optimal for the problem. And you can write it very concisely in a nice little concurrent program. So also I should mention some bad programs you can write with chemical reaction network, chemical reactions, and some of them that do not correspond to any kind of physical reality. So first of all, if I show the program x goes to y, the simple instruction x goes to y to a physicist, it will immediately say, that violates thermodynamics, it's invalid. That because in thermodynamics, every reaction must have an opposite reaction. But here you can say, okay, there is a little tiny reaction going the other way, and we just don't bother writing it down. A little bit more critical is this one here. This violates conservation of mass. You have 1 kilo of X, you get 2 kilos of X for free, apparently. Well, here you can say, well, let's assume there is a reservoir of mass, let's call it A, and this reaction is an abbreviation for A plus X goes to X plus X, so the mass comes from A. And this is accepted even in chemistry because if it's an open chemical system, there will be inflow and outflow of mass. And so the system itself will not preserve mass given the inflows and outflows. So this is a fairly common situation. But the next program is really bad. This says 2x goes to 3x. Well, this is worse than this one because in this case, we had that x was going to infinity, but in infinite time. So that was okay. But this one, the amount of x reaches infinity in finite time, even just 1 second here. So this violates finite density. So basically, it would produce a black hole if it was something actually physical. And so this we should exclude from our programs, but unfortunately, it's undecidable, of course, whether a chemical program will have this kind of graph. So it's probably not worth worrying about that. So what are the so what can you actually program with chemical reaction network? Well, if you take this definition of finite stochastic CRNs, which means that we have a finite set of reactions over a finite set of species with a stochastic activation rule for the reaction, the running parallel stochastic, whichever is faster is more likely to run. Then this system is not Turing complete for the same reason that Petri nets are not Turing complete. The reachability is decidable. But unlike Petri nets, there is this notion of speed of a reaction. And this notion of speed lets you implement timeouts and delays. And this actually gives you a way to approximate Turing completeness. So you can actually reach Turing completeness in the limit, which is an interesting class of computational system, which I don't think had been investigated before in this sense. It was being shown in this paper here. So in fact, they're very powerful. They're very, very powerful system from the digital point of view of programming algorithms based on discrete molecules and things like that. Now, if you add polymerization, which means they add the capability to chain molecules, to stick molecules together into a chain, well, then you right away you have a Turing tape, and then you're fully Turing complete. But strictly, the chemical reaction networks are not Turing complete in that strict sense. So this is about, in a sense, digital computing, what you can do with algorithms and discrete number of molecules. But probably chemical reactions networks are more suitable for analog computing, where you have not discrete molecules, but you have concentrations of substances. So that's a real number quantity. And the question of what can be represented, what kind of system can be represented in this framework becomes the question of investigating what kind of dynamical systems you can represent. Now, a dynamical system is anything that can be characterized by a system of differential equations. Let's define it that way. And there is a subclass of dynamical systems which are called elementary, which are actually not at all elementary, but they're called elementary. And those are the dynamical systems where the differential equations on the right-hand side include only polynomials, trigonometry, exponentials, fractions, and their inverses. So excluding any other kind of weird mathematical function that you might find in some differential system. But for example, you can do a lot of physics this way. For example, the equation of the simple pendulum on the right-hand side has a sine function, but this is okay. We are still in the elementary systems. In biology, you have enzyme kinetics, which has fractions on the right-hand side. Still okay. It's still fractions here. In meteorology, you have chaotic systems like the Lorentz attractor. And this is just a polynomial system, in fact. There is it doesn't take any, it's not difficult to represent as a system of differential equations. The polynomials, no problem there. And also chemistry, the law of mass action of chemistry implies that all the differential equations basically are polynomial, essentially, again, unless you are dealing with enzymes like here, and then you go to some kind of more complicated kind of kinetics. So this captures a huge class of dynamical systems, so we don't have to worry about expressing it very well. And the first thing you do, the first thing that people did a long time ago, was to try to reduce this complicated class of elementary systems to something simpler. And basically, there is an algorithm called polynomization, which takes any elementary dynamical system and reduces to just a polynomial dynamical system exactly. This is not an approximation, it's just an exact reduction obtained by adding more variables to your system of differential equations. So this was done, essentially was done originally by Shannon, because he wanted to reduce complicated differential equations to simpler differential equations so he could run them on his analog computers of the day. But Shannon did not write down the algorithm, nor did any mathematician after him that I can tell. So the first time I found this algorithm is in this paper here, where they were doing something completely different, but on the way of doing that, they wrote down the polynomization algorithm. This has now been implemented a few more times since then. So this is the first step to go from complicated dynamical systems to something simpler. And now we are into polynomial systems. So let's look at an example of a polynomial system. So this system of two equations here. So the time derivative of S is C. The time derivative of C is minus S. If you solve the system of differential equations, you get sine and cosine functions. So you have a nice oscillator, typical canonical oscillator. So let's say we want to implement this oscillator with chemistry, which is quite common because in chemistry, in biology especially, lots of things oscillate. In chemistry, there are some interesting systems that oscillate that they're only discovered in the 1920s. They're quite recent. So oscillation is an interesting problem for chemistry and biology. So let's say we want to implement this with chemical reactions. Well, the first problem is that sine and cosine go negative. So we can't have that because chemical concentrations cannot go negative. That can only be positive. So what we can do here is to transform the system of differential equations into a positive one, basically map it into the positive quadrant. This can be done systematically by splitting each variable into two. So S becomes S plus and S minus, C becomes C plus and C minus. And after you've done the variable substitution, you expand whatever you have on the right-hand side here, and you end up with a bunch of monomials. And you can refactor those monomials into a new system of differential equations, which have twice as many because we split the variables. But now all the quantities are positive because what we've done here, we've encoded a quantity which can be positive or negative as the difference of two positive quantities, because all the initial conditions are going to be positive, so they're going to stay positive. So now we have a new system of differential equations on these new variables, and if you look at the if you plot the difference of these trajectories, then you recover the original trajectory. So the solutions of the system, by taking these differences, the same as the solution of the original system. So this is called positivation, this step, and it was first done for linear dynamical systems, but the same procedure exactly applies to also non-linear dynamical system, which of course happen quite commonly in chemistry. So now we are okay, we are in the positive quadrant, we don't have to worry about that anymore. And now we would like to go from this system of differential equation to actual chemical reaction somehow. So how do we go from here to there? Well, again, there is an algorithm, which I will not describe in detail, but it's in this paper here. And this procedure is called Hungarization informally, because this is a people from Hungary. Basically, for each monomial in the right-hand side of this system of differential equations, you get one chemical reaction. So you just monomial by monomial, you get chemical reactions. This only works for a subclass of polynomial differential equations, but it so happens that if you first do positivation, if you first do this step, then automatically this system you obtain here satisfies the restrictions, the requirements of Hungarization. So you just apply that step without thinking. And now we have chemical reactions. And again, if you run these chemical reactions in a simulator or whatever, and you look at the differences, you end up with the same traces. Now you have negative values, where you're looking at the difference of two positive values, which can be negative. Okay, so so this is good. What about so this is a simulation. What about real molecule, real physical existing things in chemistry? Well, there is a whole set of technologies in DNA computing which allow you to go from an arbitrary set of finite set of chemical reactions like this one here to a set of molecules, in particular DNA molecules, that when combined, when mixed together, they will produce the same kinetics as this set of reactions. So you start from the reactions that talk about S's and C's, which you have no idea what they are. So if you give this reaction to a chemist, he will have no idea what to do with them, because it doesn't know what kind of molecules could possibly have those reactions as the kinetics. But in DNA computing, we can, from the reaction, we can systematically determine DNA structures that, when combined, will produce the kinetics of these reactions. And then again, you can run that into a wet lab and get the same trajectories, hopefully, in your test tubes and whatever. So this process is described in this paper here. And this works up to, so until here, it was all exact reduction. Now here, there's an approximation, because this DNA molecule do multi-step execution of each, multi-steps involving each reaction. And so to emulate the mass action kinetics requires an approximation, but that's, you can approximate arbitrary precision. So to summarize, now what we've done is started from an arbitrary elementary dynamical system, and through this chain of reductions, we now have physical molecules that we can run in a lab and obtain the kinetics. So for example, what we actually did experimentally was to take the approximate majority algorithm, which I showed you before, and for each reaction, we produce the DNA structure, which are these double-stranded and single-stranded things here. We mix them up into the lab, and these are the actual experimental traces showing that, in this case, X was winning the competition between X and Y populations. Now, this can also be extended a little bit further to differential algebraic equations. So in electronics, in electrical circuits, meaning just resistance, inductance, and capacitance circuits, well, they cannot be handled simply with differential equations, because you have, well, differential equations due to, for example, Faraday's law of induction, but you also have algebraic equations due to Ohm's and Kirchhoff's laws, and they intertwine, they combine into the description of the chemicals or the electrical circuit. So it's actually more complicated than differential equations. And in the case of linear differential equation systems, which are the ones that come from these RLC circuits, we've shown that you can actually do the similar reduction of what we did before. Again, it involves an approximation, but you can take an arbitrary RLC circuit from textbooks, like a filter here, and systematically translate that to a chemical reaction network, which is not that much more complex in this case, that does the same thing as this electrical circuit, and therefore implement, in a sense, the same function. And this is described in here, and this paper also contains some more details about the previous steps of the process, which I described in the previous slides. So this is pretty much all I wanted to say. What I wanted to emphasize here is that this implies that, of course, we know that biology can achieve a lot of highly complex behaviors, including neural networks and so on, and the real ones. And one of my wonder is this because there is a whole collection of tricks that biology plays, and in each case there is a special trick that achieves a special effect. And the answer here is no. There is a completely systematic way to achieve almost arbitrary complexity that can be implemented by biological entities through chemical reactions and whatever other means which are even richer that biology has at its disposal for achieving interesting behaviors. So chemistry is not just a bag of tricks. Is a uniform tool to implement complex behaviors. It is Turing complete in this, at least in this limit, or even really Turing complete if you add polymerization. It's also Shannon complete. I'm making this term up, by the way. I don't know if it's the standard, but you can emulate basically any dynamical system you want. And any of this collection of chemical reaction networks can be implemented with physical molecules that you can run, synthesize and run in a physical lab and measure the results. And this is now approaching a nice situation where we can have some kind of a notion of something we want to model or something we want to understand. We can translate it to chemical reactions, synthesize the molecules we want to. We need to for those chemical reactions, run them into a lab, then look at the results. In the case of DNA computing, you can sequence the result to see what happened in your experiment. And by sequencing the result, you get back to the digital domain, because now you have digital sequences of DNA nucleotides that you can then change any way you want and feed back into a synthesizer that will synthesize new DNA molecule again. And you can go into a closed loop, iterating on your dynamical system for whatever purpose you might want to have. So we can achieve essentially full automation of the scientific investigation in this kind of domain by chaining the reduction of chemical reaction network to molecules and the interaction with dynamical systems. Okay, so this is all I wanted to say. I'll just finally show you a little movie. Suppose you want to implement the reaction X plus Y goes to Z with DNA. This is DNA. These are double-stranded DNA, and this is single-stranded DNA. The X's and Y's are actually, sorry, they're A's and B's. These are the inputs, and they're single strands of the DNA. And these are the double strands are the gates. And and this is what the way this reaction is implemented. There's a shuffling of DNA strands that eventually produces the output Z. So X comes, Y comes. There's some shuffling with the existing double strands, more shuffling, and out comes a Z. So this is the kind of thing that happens when you run these DNA systems in a lab. And I will just cut it short here. And if you have any questions, please go ahead.
Okay, so thank you very much. So any questions, please put it into chat. Our time is probably quite tight at the moment, so we're not going to, unless somebody having a burning question, we will not have that question and answering session.